perhaps we don't know the pi and we want to calculate it. So let's do this exercise. Let's do this one in code really quickly. So we're gonna start a new program here. I'm gonna put this one on the left here just to have it a little bit clear. Okay, so it's just above my head over there. So let's write a function here, calculate pi. And this function will have to do a sum of some expression. So let's calculate first this, let's extract and do a function to calculate just this expression, and then we'll sum them. So we'll have a function, let's have a function, calc expression, and expression takes basically is based on k. We'll use k as argument here. So we'll just well, we can have it like that. Well, let's use several variables just to make it a little bit simple. So we'll have this in a variable, this in a variable, this in a one, this in a one, and this one in another one. So let's start with the first one. Let value 1, it's 1 over 16 to the power k. Actually, we have a function, and now we can use the terminology called pow, that we put 16 and k as arguments, and actually we'll raise 16 to the power k. And we'll return that value, and we are using this one in an expression, so we can say over 1 over 16 to the power k. That's first value. Let's take the second value here, this one, which is 4 over, and we'll put in a parenthesis 8 times k plus 1. All right, the other one, the v3 there, it's 2 over 8 times k plus 4, semicolon. The v4 equal 1, this one 1 over 8 times k plus 5, and the last one equal 1 over 8 times k plus 6. Whew, lots of typing. I hope I put them right. So now we have to return, and will be v1, which is the first part here, multiplied with, and inside the parentheses we'll put v2 minus v3 minus v4 minus v5. I think I got them right. v1, and inside the parentheses v2 minus v3 minus v4 minus v5. I think I got them right. So this is an expression, and what we can do, we can test it right away just to make sure that we didn't introduce an error here. So before we finish everything, we can calculate an expression for 0, perhaps for 1 and 2. Something like that. We print 3 numbers. And oops. This one is not printing, it's just returning a number. So we have to print it. Print ln of this one. So let me quickly wrap it in println like that, and if I run it, I should see, well, as you can see, the first one returned 3 point something, so probably when these numbers will get up, they'll converge towards 3.14, which is pi. So let's see, looks okay. So let's do this sum here. So calculate pi, maybe should take as an argument an n. We cannot go to infinity, so we'll calculate pi up to 100 iterations. So we're gonna do like last time, the algorithm for summing, we're gonna use like we used last time, so refer to the previous lesson. We'll start with a sum initialized with 0, and then we'll say for let k, and we can use k again here, it's fine, we are in another function, we don't, this k is totally isolated inside this function, sits there, is not interfering with this one, so we can use this one, is 0, k less than n, again we are going up to n, not infinity. It would be bad to go to infinity, our computer will freeze and crashes and we'll have to reset it. So we are adding to the sum, well, we are adding to the sum this expression actually, so we are invoking this function. And I'm using here, I could have taken it in a variable, I could have said value is calc expression like that, and sum then is plus v, but I can also use directly in an expression since it's a function that returns a value. And we are passing as an argument k. Now notice, we are passing the actual k here, the 0, the 1, the 2. That one will arrive inside this function and will be used here and return a value. All right, so looks okay, but this function needs to return something. It needs to return the final sum. And now we have two functions. They don't print anything. We have to, let's take in a variable here. Pi value equal, I'm just saying pi value because we have, there is not pi, there is an uppercase pi defined, but let's say pi value. Calc pi, and since we are running on a computer, we can make it calculate 100 of these expressions, and then let's print. Let's see the result. Ta-da-da-da-dum! Ta-da-da-da-dum! We have pi on the pi day calculated with this formula by Bailey, Borwin, Plouffe. I think I didn't say it correctly, but well, that was quite interesting. Calculating pi. So how do we approach this one? We see here that basically it goes 3, 5, 7, 9. We notice how that series goes. So perhaps we can make a function called pi again. And obviously here we'll have to do minus plus minus plus. So we'll have some sort of a initial value 1 from which we subtract, add. Yeah, so we can have a initial value. It's not really a sum, but I'm still naming it a sum. Is this 1, and then we subtract 1 over 3, we add 1 over 5, we subtract 1 over 7, we add 1 over 9, and so on and so forth. So let's do a for loop, and we'll use an I variable that starts at 3, perhaps. We subtract 3, and this one they repeat. So the next one is with 4. The step is 4, basically what I'm saying. So I less than, perhaps we should also place here an n. We go up to a certain value, and then I plus equal 4. So we go to the next part here where the series starts to repeat. So from the sum, we subtract, this time minus equal, 1 over I, which should be 1 over 3 initially, and then to the sum we add 1 over I plus 2, which should be 5. When the loop repeats, I is 7. I think we are right. I'm not sure exactly, but let's hope we are right. So this one will calculate the entire thing, but in order to return pi, we need to do 4 times that thing, because this is 4 over pi. So basically we are returning 4 times sum. Let's see if we did it right. If not, we'll abandon the program. Let pi value again. Let's say calculate pi. Let's choose an arbitrary value for n to go up to 100. This series sometimes converge for big numbers. So let's see. ln pi value, and let's run it. Moment of suspense. Well, I think it's still a success. It's not 3.14, but we are getting closer to pi. Let's try to go up to 1000. It starts to converge. So apparently this, let's go 10,000. This is a very big number, by the way. When we put here 10,000, we'll have a very big for loop. We'll cycle through a lot of numbers basically to go to 10,000, but let's see. Yeah, 3.14. We got already the third decimal, should be 5, this one. So let's go more, maybe 100,000. No, we still get 6. I should be 5 here. Let's go to 1,000,000 here. Not only that we got the 5, but I think after 5 comes 9. So we got pi with pretty good precision, but well, the difference is that this series converges much slower than the other one. But nevertheless, we calculated pi again, and it was a nice exercise, not only to create a function, but also to remember how to use for loops in here. So calculate pi 2, and I'm thinking of a canvas. Let me switch here. I'm thinking of our canvas. But before that, let's place a circle here. And I'm gonna place it in this corner here. And we know the area of a circle, it's pi r squared, right? So if we'll have a way to measure the area, and of course we'll know the radius because we draw the circle of a certain radius, and if we have a way to measure the area, then pi is area over r squared. So we can find basically the pi by measuring the area. Imagine that you are on a field and you need to know pi, and well, the way you'll do it, you have some small tiles and you start placing tiles in a circle as closely as possible, but you form a circle, and then you know that each tile perhaps is a 1 square foot or something like that, and then you count the tiles, then you determine the area, you measure with the ruler the radius, and you divide them and you figure out the pi. It's kind of a pointless exercise, but still gives us a little bit of chance to play with coding nevertheless. So the way I'm thinking to approach this one is to basically imagine that we have a circle here and we don't even have to draw it. I'm just using the left corner because the coordinates is 0, 0 here, and it will be a little bit much easier to do the math. And this circle, let's say, has radius of r. So if it has radius of r, has an arbitrary radius of r, right? So we should have r here, we should have 2r here. We are putting the circle inside the tight square, so 2r here. So what it means to basically to measure the area. Imagine that this one, of course, we are not on a field and we don't have tiles, but inside this circle, these are made of tiny, tiny pixels. So we are actually counting how many pixels are inside the circle. And by counting how many pixels are inside the circles, and I drew the pixel a little bit bigger here, it's basically, we know the area in pixel square, if you want. So if we know the area of the circle in pixel square, we can divide it by radius square and we figure out the pi. So how can we count the pixels inside a circle? Well, what we're gonna do, use a nested for loop to scan the entire rectangle, the entire square. It's actually a square. This guy here, the one that contains the circle, it's actually a square. So we're gonna use basically a nested for with an x and y to loop through all the pixels inside the square. And we saw last time that it's very easy to loop rows and columns with a nested for. So we're gonna use the same approach. And we loop through all the pixels, but the question is, and then for each pixel, we're gonna measure the distance from the center to that pixel. And the center is actually at coordinates r here. So this is the center, it's the coordinates r. Since we are choosing the radius r and we're placing this in the top left corner at 0, 0, the center is radius r. So what we are doing, we are calculating the distance between an arbitrary pixel at coordinates x, y, and the center at r. So what we're gonna do? Well, if the distance is less or equal to r, if it's less or equal to r, then what it means? It means that it's inside circle. Because all the pixels inside the circle, perhaps we should pick a pixel somewhere here. See? The distance from center to this particular pixel is less than radius. And the maximum distance is when it's actually on the circle itself, and then that distance will be the radius. Any pixel from outside, for instance from here, well, for sure the distance will be bigger than radius. So therefore we are going again on this for loop, and we're gonna loop and loop, loop in loop, and then for each pixel we calculate the distance, and now we have a formula for the distance. We just did it before, or you can use the built-in one. And then if those pixels we determine that they are inside the circle, we add them to the area. Once we calculate the area, we divide it by r square, and we should get our pi. So let's get started. We have a little bit of work to do. So, so we'll not, perhaps we should start with a function, calculate pi, and basically, yeah, so basically this, let's say, a circle, we start with a circle of radius r, right? That we want to use as a measure. And what we're gonna do, we'll have two for loops. For let x equal 0, x less than 2 times r. Remember that we're putting in a square of 2r radius, x plus plus. And we go for the other one, for the vertical as well. Also, we go down to 2r, y plus plus. And at this point here, we are iterating through all these pixels in this 2 by r square. Let's figure out the distance between x, y, and the center. So the center should be at r coordinates. And what we can do, we can make a decision here, saying if the distance is less or equal than r, then means it's inside the circle, so we increase the area. So perhaps we should have a variable here, let area. So yeah, let area. Initially it's 0. We assume the area is 0, but once we encounter pixels that are at this distance, we can basically increase the area. So we can say if the distance is less or equal than r, area plus plus. We increase area once, right? So area, boom, boom. Like we encounter one new tile. We counted when we place those tiles on the field, we counted one more tile. So we encounter one more tile. So here, after we finish the looping, area should contain an arbitrary number, or the area of the circle. So if we want to calculate pi, because this function is called calculate area, calculate pi, not calculate area, we should just return area divided by, let me look to my notes again. Yes, and they were r square here. So divided by r square. I'm gonna just use it like that. So let's see the result here. So let's take in a variable, calculate pi for a circle, maybe with a radius 300, and we print the value. Let's see the result. Very close to pi, actually with 3 decimals here. Now, of course, in order to increase this one, you need to have basically a bigger circle, and you'll converge closer and closer to pi. So this one is calculate pi version 3. Just before we close this exercise, let's also visualize these pixels. Let's put a pixel with using the point instruction. By the way, this didn't happen on a canvas. It's on a virtual model of the canvas in our memory, inside computer memory, somewhere virtually. This didn't use any drawing instruction on the actual canvas. We didn't use circle, we didn't use point, we didn't use any instruction. All these distances were calculated virtually, like we assume there is a canvas, we assume there are points, but all these were just pure mathematical calculations in this program. But now we're going to use a point at x and y coordinates and actually plot the points on the actual canvas. Let's see what we look through. Actually, if we place all this, will be a rectangle, I guess. Yeah, it's a rectangle because we plotted all the points. But if we place this instruction inside the if, and again here I didn't follow the advice, even if you have only one single instruction, place it in a block, because if you want to add the second one, we need to make sure it goes in the block. So here, if the distance is less than r, we are increasing the area, so must be inside circle. So let's put a point there, and we have a circle. See? So all these points that we plotted right now, we also counted towards that area. So we counted all these points here, and that is our area, and we divided that by r squared, and basically that gave us the answer to pi. I'm commenting this line since these points are so many, the program becomes slower than without it. So right now it's a little bit faster, much faster as a matter of fact.